In this talk, we will talk about sampling and confidence intervals. This is the recall of the definitions from last time. So I have a box that has some blue balls and red balls. And I call this the population. It's all the balls that are in the box. Right? If we take one ball out of the box, we call it a sample. So we are sampling what's in the box. And so the sample is one of the balls, and then we observe how the ball looks like. So that's called the observation. We observe if it is red or blue. Right. And what you would like to do is say something about the population by observing some sample. Right? We do not know how the whole population looks like. Usually the population is just too big to check everyone. Right? So what we'd like to do is get a sample and decide something that happens for the whole population. With a sample, you pick 100 balls out of the box. You look how many of them are blue, and then from that you can try to decide what's the proportion of blue balls in the whole population. If you repeat this experiment many times, so let's say I pick the 100 balls, scan blue out of them, and do it 100 times, then I will get some histogram here where I plotted how many times I got blue balls. Right? So there were some attempts where I got 45 or less blue balls, and sometimes I got 75 or more. Right? But the outcomes are strongly concentrated around, let's say, 60. Right? And that's how I cooked up the data, that I was saying 60% of the balls are blue, and then tried to do this sampling and see how many blue balls come up. And the more experiments you get, the more closer you get to this normal distribution. What we saw was the normal distribution on previous slide. There are many different distributions how your data could look like. They could be uniform, or they could just be on two extremes. You can have some exponential decay. You can have the bump move to the left, right. There are many different distributions. Right, so you don't have to know all of the distributions. Just make sure that the data may fit some of these curves, and then you may have some nice properties about it. We'll work with the normal distribution. So here's the normal curve, and what does it do? On the x-axis you have multiples of the standard deviation, right? And from the mean. So if the mean is 0, then you are in the middle, and then the multiples of standard deviation are on the x-axis, and the percentages in the middle is saying what's the percentage of the samples that belong to that region, right? So maybe minus half of the standard deviation to plus half of the standard deviation is 19.1% times 2. Right? So that's how many samples are covered. So about 40%. And if you go from minus 1 standard deviation to plus 1 standard deviation, you have about 70% of all the samples are covered in there. So how to use it? He will make a example. Right? I would you take a sample data, and you try to fit the normal curve around it, and then it will try to tell you how the data may look like in reality. Right? For us, we'll do it with pickles. Let's say that you want to make jars for pickles, and you would like to make jars that fit most pickles. Some pickles are very long, but if you try to make jar that fits every pickle, including the biggest pickle that appears at the state fair, maybe that's not worth it. Right? So maybe if you can fit most of the pickles, then you will be fine. Right? So what's the most of the pickles? Is the question. Right? Here are a few things that we will need to calculate. One is mean, the average of a sample. Just say all the values from the samples. If you have n of them, you divide by n. And then you have a standard deviation where you have the true mean, and you subtract the value xi from the true mean, you square it, and then you take 1 over n. So you have average of the square differences from the mean. The fun thing is that if you have a difference from the mean, either positive or negative, with the squaring it doesn't matter, right? Either will work. And you can notice that because you square things, you get units square if x had any units. So to get it down to the no units or the original units, you have to take a square root. That's why the standard deviation is with the square over there. Right. But often you cannot really calculate the standard deviation because you don't know the mean. So there is something called sample standard deviation, where you calculate the mean of the sample. Well, denoted by x bar, and then the sample standard deviation is differences from the sample mean squared, and you don't take quite average that you would divide by 1 over n, you divide by 1 over n minus 1. And by dividing by n minus 1, if you have fewer samples, your deviation will be a little bit bigger. So it's somehow a penalty for not knowing what is the true mean, and if you have fewer samples, you try to correct for this. Alright, so let's go back to pickles. So you want to find average length of the pickles to make jar. All pickles have length mean mu and variance sigma square. Right. So now we randomly select n pickles and measure them, and have measurements for the pickles x1, x2 up to xn. So what I would like to do is find the sample mean, and now I hope that the sample mean is the same as the true mean. Right? Maybe yes, maybe no. So how confident are we that if we do the sample mean, that we will find the true mean? Right? The samples is what I can do, but what I really want is to have the real mean of the pickles. So here is the sample. You can consider length. This is a made up length, or what is the mean of the sample, what is the sample standard deviation, and then try to see what is the actual mean. Right? The nice thing is that you can either try to calculate it by hand from or you can use Python, and if you just put it into data frame, it will tell you the mean and sample standard deviation. Alright, so now we did this test once, so let's try to do this test again and again and again. You can keep doing this test over and over. And the question is, how are the means of the samples distributed? Right? And in the repeated sampling, the distribution of these means is normal. They are normally distributed, where the mean of these sample means is the true mean. Right? And there is some standard deviation that is sigma over square root of n. So maybe if we have the pickles and we would try to calculate the means or the sample means of the pickles, and we keep creating more and more samples. We do the sampling once, then we do it again and again and again, then we would get this histogram. Here is a picture how it looks if you put the normal distribution over it. Right? So, alright, so what happens is that we have our sample, we calculate the mean, and we would like to figure out where the true mean is. Right? When we do the calculation, we are likely to be within 2 standard deviations of the true mean. Right? That's what is the explanation that you have the means that we created, the sample means, normally distributed around the true mean. So most likely you are within the 1.96 of the time standard deviation of the true mean. So your sample mean minus the true mean is at most 0.196 the standard deviation, with probability 95%. Right? So what you can do is you can solve for the true mean by taking the mean that you calculated, calculate the standard deviation from the data you have, and you make a bracket of so your mean minus 1.96 times the standard deviation to your mean plus 1.96. And now you have confidence 95% that the true mean is inside this interval. Right? So the confidence means that it's not a probability that the true mean is in the interval with 95% chance. You are just confident that it is there with 95%. In other words, it means if you would repeat the experiment over and over, you would try to do the samples and calculate the means and get the interval for the true mean, then in 95% of the times, the interval you give would contain the true mean. That's what it means. Right? So you are confident in the procedure that you did, that is 95% confidence you can say that you have the true mean. But there is no probability at that point. Once you say this is the interval, and once you say this is the true mean is there, and you fix the interval, either it is in or not. There is no chance anymore. The process you get to it has 95% chance of success. Okay? Of course, the true mean can be outside of your confidence interval. So 5% of the outcomes would give it out, right? But yeah. Here is an experiment. So what's the mean height of student at Iowa State University? Right? So what you could do is try to find a sample of students and calculate the mean, the standard deviation, and it will give you an interval that will contain the true mean. Maybe, right? That you'll have some 95% confidence that the interval that you come up with contains the true mean. And how do you sample the students? Maybe you can pick a room and measure all the students in that particular room and calculate the mean, standard deviation, and then you can try to say that the true mean of the heights of the students at Iowa State University is plus minus 1.96 of the deviation from the mean you calculated. And you have 95% confidence that that worked. Right? But it may happen that you will be outside of the correct range because you may pick the locker room of the ISU basketball team, right? And suddenly you will get heights that are much bigger than the typical heights of students, and then maybe the confidence interval, you will still have 95% confidence in the interval, but the interval will be wrong, right? The way how you were doing it, find the room on campus and measure the students, was a good approach, but it fails. There are cases where it may fail. Right, here are some questions on how to interpret the confidence interval. Having 95 confidence interval, 6.96 to 1024, means that if we repeat the sampling many times, 95% of these intervals that we obtain will contain the true mean. That's what it means. It does not mean that 95% of the data is inside of this interval. Only the mean, right? And it doesn't mean that there is a chance the 95% that the true mean is in this interval. There is no chance anymore. The true mean either is there or not. There is nothing random anymore, right? Only that repeating the sample link will give you 95% chance that if you get the interval from the sampling, then it contains the true mean. So here is a question. Having 95% confidence interval, is it true that 95% of the data is in the confidence interval? Answer is no. Only the mean is something that you talk about. Only the mean has some guess that it will be inside the interval. Rest of the data, it says nothing about the rest of the data. Right? Is it true that having 95% confidence interval means that there is 95% chance that the mean is inside this interval? The question, yes, no. Well, it's a tricky question. The answer is no, because the question is wrong, in the sense that there is no chance anymore. Okay? The true mean is something that's a number that exists, right? And if you show me an interval, then the true mean is in it or not. There is no chance anymore, right? Having 95% confidence interval means that the process of creating this interval has 95% chance of success that the mean will be inside this interval. But once you fix the interval, chance is gone. Right? I'll show you an example on the next slide. Here's the example that should illustrate the problem with confidence intervals. Okay? So here we'll play a game. Right? I'll take a piece of paper and write a number between 1 and 6 on the piece of paper. And I will not show you for now the number. Right? So I have my secret number, 1, 2, 3, 4, 5, 6, one of those. And now what's the chance that if you roll a dice, you have the same number as me, right? So if you roll a dice, you have a chance 1/6 that you get the same number as me, right? But what happens after you roll the dice? You roll the dice and write the number from the dice on your piece of paper, right? So now I have a piece of paper with number between 1 and 6, and you have a piece of paper with number between 1 and 6. And the question is, what's the chance that they are the same? Right? Now that's not a correct question. There is no chance. Either they are the same or they are not. We just don't know. Right? The way you obtained your number, you had a chance 1/6 that you get the same number as me. But the moment you write it down, the moment you finish the experiment, when you roll the dice, after you roll the dice, either you got it or not, right? No more chance. Maybe you just don't know, right? If you have the same number or as me or not. But no chance. Same with the confidence interval. When the process of getting the confidence interval has a chance 95% that the interval in the end will contain the true mean. But once you have the interval, it doesn't mean that you have the mean in it. Right? Here are some other interpretations of it. Having 95% confidence interval, does it mean that if you randomly pick x, it will be in this interval with 95% chance? Yes or no? No. The only thing the confidence interval is talking about is the mean of the values x. It doesn't say anything about the x itself when you pick a random number. So this is not the right interpretation. Here is a question about wrong studies. Right? Many studies have confidence intervals, right? And say, oh, we've found something and we have 95% confidence that what we did is the right thing, right? And the question is, how many of them are actually wrong, right? If you have 100 studies, 5 of them will be wrong, not because like some malicious intent, but just because of the nature of the mathematics behind, right? Just as you have 95% confidence, so in 5% of the studies, maybe the interval is wrong, right? If you have 1,000 studies, then it's 50, right? If you have million studies, then it's 50,000 of them are just wrong, right? So one has to be careful. Sometimes it makes sense to repeat studies if they are very important, because it's a trouble with experimental science. Is a interesting problem of how do you sample and what are the effects of sampling. Something to be aware. So let's say I would like to look at emails that are sent and received at I-State edu addresses over one academic year. There's too many of them, so I would like to take a sample, right? And look at some sample emails and see. So how do you take a sample? So you have a lot of email data, right? That you can include, like sender's name, text name, like all the and what will sampling introduce is some bias, right? you can say, how do you select the emails, right? Will you have 1/10 of all senders at random, and you will look at 1/10 of the people, or you will look at 1/10 of all the emails that come from every day, right? So it will give you potentially very different answers. And the trouble is the number of emails people send. Right? Sometimes there are people that send very few emails. So if you select those people, you will get no emails at all. And sometimes there are people that send lots and lots of emails, and if you send them, then you get way more emails. And also, if you just send like emails randomly, maybe you will get them mostly from the people that send the average number. You kind of miss the people who send a lot, or you may not see the people that don't send any, right? So it's something that one should be aware of. Okay, so why do we sample? We sample because we cannot ask everyone in the population, but sometimes sampling comes with biases. Right? So what one needs to ask is, if you are having sample, what's the relation between the sample and the whole population? And how do you know that you have a good sample? Right? You want to somehow uniformly, somehow nicely sample population. There is a story, Literary Digest, that made a history of bad sampling, right? So it was for presidential election between Roosevelt and London in 1936. The magazine polled 10 million people. Over 2 million replied, and the clear winner was Landon for president. That was the poll. And then, when the voting actually happened, Roosevelt won almost every state. But what they did in the sample looked like overwhelming victory for Landon. So what went wrong? Right? What went wrong? There are different things that can wrong, right? So one is who was in the sample. The sample was magazine subscribers, automobile owners, telephone owners. Those were people who have usually higher income, and also only some of them chose to respond. Right? So this led to the sample that was not really sampling the population uniformly, whatever that word means, but it was sampling only particular part of the population, and despite having a huge sample size, it was not useful because it didn't capture the whole population. It was a competition or competing prediction which correctly declared the winner, and they needed only 50,000 for their sample. So this was a big surprise, and it led to refinement of polling techniques. Just you need to have a good way how to make sure that you capture all people in the population. Ideally, you would want everybody to have an equal chance to be included, but that's probably hard, and they screw it up. Right? If you want to learn more about confidence intervals, there is a video on them from StatQuest. I highly recommend.